Hi, it's me, Tim Dodd, the Everyday Astronaut. Rockets are huge, complicated, and expensive. As a matter of fact, the rocket that took humans to the moon, the Saturn V, was 111 meters or 363 feet tall and had more separation events than dating teenagers. I actually didn't mean for that one to happen. So why do rockets always split themselves up into multiple parts? Isn't that complicated and risky? Why throw so much of it away? I mean, there's got to be a better way. Well, how about if rockets were only one stage? How awesome would that be? Well, this idea isn't new. It's called single stage to orbit, or SSTO, and it's often considered the holy grail of rocketry. Well, today I'm gonna smash that holy grail and explain why I think SSTOs suck. In order to drill this point in, we'll teach you all about the tyranny of the rocket equation and help you understand why every orbital rocket, well, ever, is multistage. Then we'll take a stroll down SSTO history and look at some crazy designs that in some cases almost worked. And not to be a huge downer, we'll also take a look at some SSTO designs that might actually work, including the Skylon spaceplane that uses that awesome Sabre hybrid engine. Okay, Everyday Astronaut versus SSTOs. Oh man, the comment section's gonna love this one. But hear me out. Let's get started.
3, 2, 1, 0, and liftoff.
So if you've ever played Kerbal Space Program, you know, that awesome computer game where you design, build, and fly rockets with these little green alien frog guys, and you get them off their home planet of Kerbin? Yeah, that one. Then you know SSTOs are all the rage. As a matter of fact, building an SSTO is kind of bragging rights and something to post on Reddit. But what if I told you I can't really think of one good reason to build an SSTO in real life? Well, there's a few potential benefits, but do they outweigh all the negatives? Okay. So before I sound like some kind of old grump here, get off my lawn, you darn kids with your SSTOs. Let's talk about why SSTOs are considered desirable by some, and why people dream about a time when launch vehicles are only one stage. Imagine a world where a launch vehicle takes off, goes to space, comes back, refuels, and does that multiple times a day. No problem. Sounds like a real-life Millennium Falcon. When most people use the term SSTO, it's inferred that the vehicle would be reusable. It would go up into space, come back down, all in one piece, throwing away only fuel to get it there and back. And again, when talking about reusable SSTOs, most people and concepts utilize a spaceplane design, a vehicle which takes off and lands like a plane. Sounds great, right? One vehicle to do it all, nice and simple. Take off from any runway, just like a jetliner at an airport, and then instead of leveling out at a boring old 10 kilometers or 35,000 feet or so, keep accelerating and increase your altitude until you're in orbit. Then when your mission's done, you just come back down from space and land on any old runway. Again, like any other jetliner. SSTOs don't sound that bad, do they? Uh-oh, have I lost my mind? Well, before we keep dreaming about our potential sci-fi future, let's take a quick look at the history of rockets to see why so far SSTOs haven't been attainable. The first liquid fuel rockets ever made were just one stage. Basically, a rocket engine, some propellant inside a fuselage, and in most cases, some kind of warhead on top. Rockets were mostly used as an advanced weapon delivery system at first, but lucky for us, they also so happen to be able to be used for spaceflight. The V-2 rockets built by Germany were the first rockets to ever reach the edge of space. In June 1944, a V-2 rocket on a test flight reached beyond the Kármán line, the most commonly agreed upon boundary of space, at 100 kilometers or 62 miles in altitude. Sure, a single stage rocket can get up to space, but what about stay in space? Well, in order to stay in space, an object needs to reach orbital velocity. To orbit the Earth, a vehicle needs to be traveling at about 28,000 kilometers an hour or 17,500 miles per hour to stay in space. Okay, so now we have a new goal for humanity. Get something into orbit. Well, on October 4th, 1957, the Soviet Union managed to place Sputnik 1 into orbit. The shiny metal ball with scary looking spiky antennas weighed only 83.6 kilograms or 184 pounds. Hey, that's pretty much my weight. The vehicle that carried Sputnik to low Earth orbit was a two-stage launch vehicle most commonly known as the R-7. This rocket was revolutionary and allowed the vehicle to drop unnecessary weight on ascent by ejecting spent fuel tanks and rocket engines that were no longer necessary. This is called staging. It was revolutionary and pivotal in putting something of any significance into orbit. Staging is the #1 cure for the tyranny of the rocket equation. The tyranny of the rocket equation is basically the diminishing returns on adding fuel. If you were to double the amount of fuel in your rocket, you wouldn't double the delta V or change in velocity. Due to now having to push around all the extra weight of the extra fuel and the fuel tank that holds it, the rocket is able to burn longer, sure, but it doesn't receive anywhere near double the change in velocity. And it only gets worse the further you go until the rocket actually gets too heavy for the engine, and the next thing you know, you're adding engines to lift the extra fuel, and so on and so on and so on. So this is where staging comes in. Once a rocket empties a fuel tank, why not throw it away? Even better, if the rocket is throttling down an engine to stay accelerating at a safe speed, why not throw away the heavy, unnecessary engines? This is what the R-7 rocket did. It was basically a good-sized rocket with 4 extra rockets attached to it. Once those side rockets were spent, they were detached in this really cool formation known as the Korolev Cross, named after Sergei Korolev, who you can think of as like the Wernher von Braun of the Soviet space program. By the way, you can still see the Korolev Cross on any of today's Soyuz launches. Separation events are often a breath-holding moment in flight. There are 2 main types of staging events. First, there's parallel staging, where multiple stages are fired and active at once, like Soyuz or the Space Shuttle or Falcon Heavy. Everyone holds their breath during staging because if a booster doesn't separate, the mission will fail. It was definitely a big moment when the side boosters of the Falcon Heavy separated safely.
Boosters, beacon. Center,
Or there's an even more complex and nail-biting type of staging called tandem staging. This is what most multi-stage rockets do. The first stage will fire first, then that engine cuts off, the first stage and the second stage separate, and the second stage fires and keeps going to orbit as a brand new, fresh rocket. Not only is the second stage basically a new, fully fueled little baby rocket, but their engines are also optimized for the vacuum of space by having a much larger exhaust nozzle. But that's another huge advantage of staging, having different engines optimized for different environments. The first rocket ever to do any kind of tandem staging was called the RTVG-4 Bumper. It was literally a V2 rocket with a small sounding rocket on top of it. It was launched between 1948 and 1950 and launched 8 times, creating a lot of valuable data on multi-staging. But this stage separation event was really hard to accomplish and almost considered impossible for a long time. That's why many early rockets utilized parallel staging. As a matter of fact, separation events, or more specifically a botched separation event, almost led to SpaceX being another forgotten aerospace company who went bankrupt after only 3 flight attempts. Flight 3 of their Falcon 1 rocket had a stage separation event go wrong when the first stage had a little extra residual thrust after stage separation, causing it to bump into the upper stage, leading to a failed mission. So if it was so coveted and necessary to make multi-stage launchers, why are SSTOs so sought after? Well, there's something to say about making a less complicated launch vehicle. So maybe SSTOs are good for something. I guess in order to see if SSTOs make sense, let's pop on over to my computer where I'll fire up Kerbal Space Program to help figure out if stages are a friend or foe. Welcome to Kerbal Space Program with Realism Overhaul. Now, Realism Overhaul is about 1 million different modifications to make Kerbal Space Program have a real solar system. It makes it a lot harder and a lot more realistic. Okay, so our goal today, we're trying to take a 1 metric ton satellite up to an orbit at 250 kilometers in altitude. So I built us a nice, simple 2-stage rocket with an RL-10 vacuum engine, which is an excellent vacuum engine. And then it has a SpaceX Merlin 1D engine on its first stage. So altogether, this thing's about 34.9 meters tall and has about 9,237 meters per second, according to Kerbal Engineer Redux. Okay, now let's get ready to take this thing off. And we'll do engine ignition. And 3, 2, 1, hip hip! Yeah, look at it go. Alright, we're gonna speed this thing up here a little bit and watch it get up into orbit. Alright, now notice I've got the map pulled up here too, so you get an idea of, you know, if this were to run out of fuel right now, it would still be coasting up to its apoapsis, its highest point, or apogee. So you can see there, you know, we got the map pulled up, and it gives us a pretty good idea of where this thing's going. Now, just like if you were to throw a ball, you know, it kind of goes up in arcs. If you were to throw it further, it would arc further and further away. Well, we're just accelerating continually, making that arc extend out even further and further and further away. That's how rockets work. Okay, now we're running out of fuel in our first stage, so we're going to go ahead and do stage separation. And now we're going to light up that upper stage. And there it goes. That's the RL-10 upper stage. And this is optimized for working in the vacuum of space. So it means it has a really high specific impulse. And specific impulse is kind of like your miles per gallon for a rocket engine. And this thing's just going to keep on accelerating now. It's going to keep on going and get itself into orbit. So it's got a long ways to go now. So this upper stage has to do a lot of work still. You know, look, it's still accelerating. And again, if it were to cut off right now and run out of gas right now, even though it was a fresh rocket, only about halfway done, it wouldn't even make it to the coast of Africa. You know, so look at, you can see on the map there, we're not making it that far yet. Okay, so we're just gonna keep speeding up and speeding up and speeding up until we get up to around 7,500 meters per second, which is about 28,000 kilometers an hour or 17,500 miles per hour. And we're just going to do an apogee kick, which is burning at the highest altitude just to totally circularize ourselves and put us into orbit. And voila, a perfect orbit-ish. That's fantastic. Now we release the satellite, and we're good space stewards, so we're going to go ahead and deorbit the stage as well, and it will burn up on re-entry. Nice and easy. There we go. Okay, well that was honestly the perfect rocket for the job. It could just barely get that 1 metric ton up into space and have just a little bit of fuel margins remaining to deorbit itself. It's perfect. It was a perfect fit. Okay, so I know what we're thinking. Let's go ahead and turn this into a single stage to orbit rocket. So first things first, let's strip it of anything that was necessary for the second stage. So let's go ahead and take off that expensive RL-10 upper stage engine. We don't need that anymore. And we don't need any of the interstage hardware either. So let's go ahead and take all this stuff off here. And goodbye. We're going to attach this back up. Well, we need to put those thrusters back down on there. And now we need to make sure we replace all the fuel that was hydrogen for that upper stage with RP1, which is the same fuel for the first stage engine. And voila, now we have about 7,155 meters per second. Let's see what this thing can do. Alright, so we've got our first version of our SSTO with the upper stage removed, ready for launch. Let's do this. 3, 2, 1, hip hip. And there we go. Let's go ahead and just kind of fast forward this a little bit. And not bad, not bad. How far is this thing going to make it? I'm very curious here. And ditch the fairings. We'll coast up. We're at that 250,000 meters of an altitude. We're going to do an apogee kick here. And we're out of fuel, and that's all the further we made it. What? Yeah, we only had a tiny little drip of fuel left over after all that. And that's all the further our satellite's going to make it, about a third of the way into the Atlantic Ocean. Let's try and go bigger. Let's add enough fuel so it can actually get into orbit. Okay, so I know what we're thinking. Let's just add some fuel, right? We're at 7,155 meters per second. We got to get that up to that around 9,300 meters per second. So let's just start stretching these tanks, shall we? So I'm just going to click here and we're going to edit this. And we're just going to make this tank taller. A lot taller, all right? A lot taller. I'm just going to keep going here. A lot taller. I'm going to be here for a while clicking. A lot taller. Well, I'm tired of doing this. Let's go ahead and stop at 602 meters tall. We're gonna need a new VAB. We absolutely smashed through the roof of this thing. This thing looks pretty cool though. Let's go ahead and load this up. Yes! It loaded! And it's not tipping over for now. Oh my gosh, that's amazing. 600 meters tall. And by the way, guys, we only have 8,800 meters per second of delta V. We still don't even have enough delta V to get ourselves into orbit. And I think there's one other problem well, besides the fact that it's insanely tall, I think there's one other thing you might realize. Oh. What? It just blew up on the pad. Oh, that's like the dumbest pencil lead thing ever. Look at that. All right, let's try and launch this anyway. I think we know what's going to happen here, don't we? Even though we only have 8,800 meters per second delta V, it's going to be way too low of thrust to even remotely take off. And there we go. It just blows up on the pad as soon as you try to let it go. So the thrust to weight ratio was way too low with that single engine. And even with that single engine, so let's see, the thrust to weight ratio is about 0.05, and you need above a 1.0 in order to actually start lifting off. So 0.05. So we'd have to add, what is that, 20 more of those engines? And we still didn't even have enough fuel to get it into space. Let's see what it will take to actually get this thing into space. Alright, so I've got an idea. Why don't we basically just do like a Falcon 9 first stage booster, shall we? So let's go ahead and first things first, stretch these tanks out quite a bit, because remember the Falcon 9 first stage booster is about 45 meters tall. And then we're gonna need 8 more of those Merlin 1D engines, and blah blah blah, better avionics, etc., etc. Kind of snazzy this up just a little bit. And what are we at here? We ended up with 8,308 meters per second. So still 1,000 meters per second under what we need to do. And now we have literally the first stage of a Falcon 9. I can't help but think that's going to be a lot more expensive. We have 9 Merlin engines instead of 1 Merlin engine and then 1 RL-10 engine. So all of a sudden we have instead of 2 engines, we have 9. We stretched the tank from about 17 meters for that first stage. Altogether, the whole thing was, what, 38 meters? And now we're sitting at, 45, 50 meter tall rocket that's way wider, way bigger, and we still are gonna fall up short. Let's launch it anyway, just to show you. And 3, 2, 1, hip hip. And again, I'm just gonna speed it up here real quick. And guess what? Look, just like that, guess what happened? We didn't have enough fuel. Even with our apogee kick there, we ended up 893.1 meters per second short of orbital velocity. We're out of fuel. There's nothing we can do now. And look, we still didn't even make it to the coast of Africa either. So we made it about 2/3 of the way across the Atlantic Ocean. And we just threw away an entire Falcon 9 first stage booster, basically. I don't get it. I would much rather have a small 2-stage rocket than a massive 1-stage rocket that can't even perform the work. And to be honest, without tweaking the variables like tank utilization or using some advanced future technology like an aerospike engine, I actually can't get this to work in Kerbal Space Program at all. Alright, so I guess SSTO rockets don't really work out too well. The math just doesn't really add up. Darn you, Sulkovsky! So I can already hear you over there saying, but, and that first but is probably, but Elon Musk said the Falcon 9 booster could reach orbital velocities. Sure it can. Now good job. You just put a $30 million piece of hardware up in space where it has no spare margin to carry anything more than a small backpack and no remaining fuel to re-enter or land. I think there's better ways to put a backpack in space. And again, Elon said that the BFS, the spaceship portion of the big Falcon rocket, is capable of reaching orbit by itself with a low payload, but using the booster, it can deliver more than an order of magnitude more payload. Well, first off, it would require firing the 4 vacuum Raptor engines at sea level, which Elon says I wouldn't recommend. But okay, combustion instability aside, let's pretend it could put 15 tons into orbit and somehow have enough margins to deorbit and safely land. So now we flew a BFS to space and back so it could deliver something smaller than a Falcon 9 could deliver. The cost of the range, the personnel, and of course the refurbishment of the ship need to be in consideration. Okay, so now let me ask you this. Wouldn't it just be better to fuel up the booster too? And since the booster experiences much less re-entry heat than the upper stage, it can be flown a lot more without maintenance or refurbishment costs. So why not utilize the entire vehicle? In the best case scenario, you just launched 1/10 the payload capacity just to save a little on gas money. Once an entire vehicle is routinely, rapidly, and reliably reusable, that's a lot of R's, then who cares if it's 1 stage or 2? So in best case scenario, 2 stages is better than 1, and in worst case scenario, 1 stage doesn't even work at all. Okay, but let's not be all poo-poo here. Let's take a look at some SSTO designs past, present, and future to see if there's anything that seems promising. Let's start off with some previously proposed and pursued SSTOs and look at why they failed. Well, one of the earliest proposals was the One-Stage Orbital Space Truck, or OOST, by Phil Bono of Douglas Space in the 1960s. Later, he proposed a reusable version called ROOST, or Roost. Another proposal from the 60s was the Nexus Rocket, which would have been freaking huge. I'm talking insanely big. It would have been 122 meters or 400 feet tall with a width of 50 meters or 164 feet. Holy moly, that is huge. Okay, so paper rockets are one thing, but how about a rocket that was actually being tested? Look no further than the DCX, or Delta Clipper Experimental, made by McDonnell Douglas. The DCX was an actual working 1/3 scale prototype of a proposed DCY SSTO that was to be capable of putting about 1,300 kilograms or 3,000 pounds into orbit. The DCX was just to demonstrate vertical takeoff and landing, and actually flew 8 times between August 1993 and July 1995, and pretty successfully. But it only reached a maximum altitude of 2,500 meters. Think of it kind of like SpaceX's Grasshopper. In 1996, NASA took the program and turned it into the DCX-A, which made some improvements to the vehicle. It flew 4 times, including a 26-hour turnaround and setting a new altitude record of 3,140 meters or 10,300 feet. Its last flight was July 7th, 1996, after landing strut failed to extend and a LOX tank leaked, causing a fire and damaging the vehicle. Despite a relatively low cost to repair and continue working, NASA canceled the program and looked to pursue Lockheed Martin's Venture Star. So let's talk about that. Venture Star is probably one of my all-time favorite spacecraft designs. See? I don't hate SSTOs. Lockheed Martin proposed a space shuttle replacement in the mid-90s and received funding from the US government to work on its development. The Venture Star ticked all the SSTO boxes. It would have been amazing, and it actually got painfully close to flying. Well, at least a subscale, suborbital version. But here's the rundown. It had advanced carbon fiber construction, a giant linear aerospike engine that could take 20,000 kilograms or 45,000 pounds to LEO. That's close to a Falcon 9. It would take off vertically like a rocket and land horizontally, just like the space shuttle. Unfortunately, the subscale X-33 demonstrator was canceled in 2001, despite being really close to flying. The X-33 demonstrator had 96% of its parts manufactured and was 85% assembled, and even its launch facility was complete. The reason for its cancellation was a long series of technical difficulties, flight instability, and excess weight. Darn you, weight! Next, how about maybe the craziest proposed SSTO of all time, the Roton? This thing is hilarious. This is a helicopter that could get to orbit, supposedly. It basically was a helicopter powered by jet tips. So some small thrusters at the end of the rotors. It would then lift itself off using low-powered jet tips spinning the helicopter rotors until the atmosphere got too low, where it then light up a rocket engine and ascend to orbit using the rocket engine. But the cool thing is, the rotors weren't just dead weight once in space either. Instead of providing lift, they would continue spinning to power the turbo pump for the rocket engine. Then, they would also be used to slow down through descent in the atmosphere and used to land softly. Apparently, it was horribly unstable when flying like a helicopter. Actually, the vehicle was found to be unflyable by anyone except the test pilots, who even then had periods of being completely out of control. Yikes. Despite a full-scale atmospheric test vehicle being built and flying, Well, sort of. The program was canceled in 2001 due to lack of funding and people saying the technology wasn't valid, and it was technically impossible on available technology. But I still love that wacky thing. It's straight up ridiculous. Okay, so what about some current proposals? It's been more than a decade since those last proposals ended. There's gotta be some new technology we can apply and make these things happen, right? Well, you can't talk about SSTOs without talking about perhaps the most alluring SSTO, the Skylon spaceplane. The Skylon is being designed by the United Kingdom's Reaction Engines Limited and utilizes an amazing combined cycle hybrid rocket engine called the Sabre Engine. Now, this is the one concept I can sort of get behind. The Skylon's Sabre Engine acts like a fairly traditional jet engine. It uses the atmosphere to its advantage. Instead of a traditional rocket that tries to get out of the atmosphere as quickly as possible by ascending virtually straight up for a minute or so, the Skylon will reach 5 times the speed of sound, or around 6,000 kilometers or 3,800 miles per hour, while pulling in oxygen from the atmosphere, just like any other jet. And unlike a traditional rocket, the Skylon can scoop up oxygen during ascent through the atmosphere. Then, when it switches to the closed cycle rocket engine, it uses onboard liquid oxygen, so it doesn't need to carry nearly as much liquid oxygen, another huge weight savings advantage. The Sabre engine has received even further funding from the United States' DARPA, Boeing, and Rolls-Royce to build a high-temperature test facility, which hopefully will begin testing this year. So the Skylon actually has some promise. But even though it's technically theoretically possible, Reaction Engines is currently pursuing non-SSTO vehicles first, much before the Skylon will ever fly. In 2017, Mark Thomas of Reaction Engines said they're currently pursuing a spaceplane as a 2-stage vehicle where it would deploy an upper stage at a high altitude and a high velocity, and then the spaceplane would turn around and land. And one more thing while we're talking about the Skylon. Remember the SR-71 Blackbird? Even though it could only reach Mach 3, it still experienced so much heat that it needed to have large gaps in its body panels, since it expanded by 60 centimeters when flying at speed. This led to it basically peeing its pants and dripping fuel when fully fueled on the runway. Now, can you imagine something that goes even faster in the atmosphere? Well, this is the 21st century after all. I don't think the Skylon will pee its pants on the runway, but the crazy high heat at high Mach speeds in the atmosphere might be a huge hurdle. I personally foresee there being many fairly substantial issues to overcome in making the Skylon actually work. It'll be amazing if it does, but for now, it's kind of stuck in that future hopes and dreams category to me. If you want me to do more about the Skylon, let me know. We could probably do a whole video on it. It's a really cool vehicle. And lastly, we should probably mention Arca Space's Haas-2CA. This to me is pretty silly. It's an SSTO rocket with a linear aerospike engine. Cool, but it's only capable of 100 kilograms or 220 pounds to orbit. Maybe they should just add a small upper stage to that thing so it can maybe put 1,000 kilograms into orbit, since they're throwing the whole thing away anyway. My big question for Arca is, why? What's the point? The only thing they claim that's an advantage is they can launch inland because there are no spent stages to fall on populated areas. I'm not sure how I feel about that. I mean, yay for aerospikes, but boo for a rocket with such a limited capability. Okay, so all past SSTOs have failed. All current SSTOs are either not going to be SSTOs or are kind of pointless in my opinion. And there really isn't much on the table for a usable SSTO in the near future without some major breakthrough in material science or propulsion. But wait, there's one more thing. So far I'm here talking all about how SSTOs failed. That's not true. As a matter of fact, one of the most famous spacecraft in all of history was an SSTO, the Lunar Excursion module. Of course it could do single stage to orbit, but only on the moon. The LEM was capable of achieving lunar orbit with only one stage, but of course that's the moon. The moon's gravity is so much weaker than Earth's gravity, and there's no atmosphere to fight against either. And then we have SpaceX's BFS, which will not only be capable of SSTO from the surface of Mars, but even have enough performance to get all the way back to Earth from the surface of Mars in one stage. Again, this is mostly due to Mars having only 38% the amount of gravity of Earth and having only 1% the atmosphere of Earth, making achieving orbit much, much easier. So maybe SSTOs don't suck. Maybe Earth sucks. It has just enough gravity to barely make it possible to achieve orbit with rocket engines, and it has that pesky atmosphere which slows vehicles down on ascent too. I still stand by the fact that as cool as SSTOs are, and as much as I do actually love them, they just don't really work in practice using currently available technology. Of course, I'm not saying that's how it'll always be, but for now, give me them stages. After all, I think we can all agree that the most important aspect of an SSTO is the reusability thing. So what if a multi-stage rocket is fully reusable, like the BFR? Isn't that what matters most? The first stage does what it needs to do, then comes back and is refueled and reused. Same with the upper stage. So who cares if the vehicle does it in one piece or breaks off into two more dedicated pieces? You can almost think of the booster stage of a rocket as a giant catapult or something, sending off a brand new fresh rocket, giving it extra velocity and altitude, and then it just comes back and lands. I think that's awesome. I can't wait for a day when orbital flight is routine and reliable and fully reusable. And the foreseeable future, I think it'll continue to be done with stages. So what do you think? Do you think SSTOs are still valid and practical, or are you on team multistage? Hashtag team multistage. Let me know your thoughts on SSTOs in the comments below. And please, spare me your Kerbal SSTO designs. It works in Kerbal Space Program is not a real argument, unfortunately. And before you tell me all about how SSTOs can take off and land on runways, remember, that's not exclusive to SSTOs. That's an air launcher and or lifting body advantage. That is not exclusive to SSTOs. But other than that, let me know if you have any other questions or things you want me to cover in future videos. As always, I owe a huge thanks to my Patreon supporters for helping make this and other everyday astronaut content possible. I owe a super special thanks to those patrons in our exclusive Discord channel and our exclusive subreddit for helping me script and research. We had quite the debate about SSTOs. If you want to help contribute, please visit patreon.com/everydayastronaut. Thank you. Don't forget to check out my web store for shirts, hats, mugs, prints of rocket launches or original artwork, and lots of other fun stuff at everydayastronaut.com/shop. As always, all the music in my videos is original. Feel free to check it out at soundcloud.com/everydayastronaut. Tell a friend. Thanks everybody, that does it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.